Dynamic line rating DLR is far from just a buzzword in the energy sector. It's a game-changing technology that can significantly enhance power transmission efficiency, reliability, and sustainability. With rising demands on our energy grids and a pressing shift toward renewable energy sources, grasping the concept of DLR is essential. As the world moves towards smarter, greener grids, understanding DLR becomes not just important, it's vital. Dynamic line rating is an innovative technology that optimizes the electrical carrying capacity of overhead power lines. Unlike traditional static ratings, which are based on conservative worst-case environmental scenarios, DLR uses real-time data to provide a dynamic and accurate assessment. This enables power lines to operate closer to their true capacity without compromising safety, leading to more efficient utilization of transmission infrastructure. The effectiveness of DLR is driven by advanced sensors and algorithms. Sensors installed on or near the power lines continuously monitor variables such as ambient temperature, wind speed, and line sag. This data is processed in real time, allowing grid operators to dynamically adjust the line's capacity. Consequently, DLR not only boosts grid efficiency but also supports the integration of variable renewable energy sources like wind and solar into the system. Overhead transmission lines are utilized for the transmission of electrical power. The current that is transported causes the conductors to heat up, while the ambient temperature and especially the wind cool the conductor. Traditionally, overhead lines are designed using conservative ambient conditions. The combination of values for ambient temperature, effective wind speed, and solar radiation are rarely exceeded. This means that most of the time, the current carrying capacity is higher than the design rating. This potential can be unlocked using dynamic line rating. Here's how dynamic line rating works to prevent overheating of power lines. Real-time monitoring. DLR systems involve the use of sensors and weather stations to monitor real-time conditions such as ambient temperature, wind speed, solar radiation, humidity, and conductor temperature. Weather and environmental data integration. The collected data is then integrated into computational algorithms that consider the various factors affecting the conductor's temperature and heat dissipation, such as wind cooling and solar radiation. Thermal modeling. Advanced thermal models are used to predict how the power lines will respond to the current flowing through them under the given weather conditions. These models take into account the line's material properties, dimensions, and the surrounding environmental conditions. Dynamic rating calculation. Based on the real-time data and thermal models, the DLR system calculates a dynamic line rating, which is the maximum permissible current that the line can carry at that moment without exceeding its safe operating temperature. Operator interface. Grid operators have access to the dynamic line ratings through control systems and software interfaces. These interfaces provide information on the current line capacity and allow operators to make informed decisions about how much power can be safely transmitted through a particular line. Load management. With the dynamic line ratings, grid operators can manage power flows more efficiently. During times of high demand or congestion, they can optimize the use of transmission lines without compromising safety. Alerts and alarms. DLR systems can also provide alerts and alarms when line ratings are getting close to their limits, enabling operators to take preventive actions such as rerouting power, shedding load, or implementing emergency measures. Improved grid reliability and efficiency. By allowing power lines to operate closer to their actual capacity under safe conditions, DLR systems help improve the overall reliability and efficiency of the power grid. This can also support the integration of renewable energy sources by maximizing the use of available transmission capacity. It's important to note that implementing DLR requires a combination of accurate weather forecasting, advanced sensor technology, computational modeling, and effective communication between grid operators and DLR systems. Additionally, regulatory and safety standards play a crucial role in ensuring that DLR implementations meet the necessary safety and performance criteria. Question is: how does dynamic line rating work? DLR utilizes an array of sensors to continuously monitor various conditions such as weather, line sag, and temperature. These sensors, strategically positioned along transmission and distribution lines, gather data on variables like conductor temperature, line angle, ambient temperature, and wind speed. Advanced software algorithms then analyze this data to determine the line's current capacity in real time. This monitoring allows utilities to maximize the use of existing infrastructure and delay expensive upgrades. Dynamic line rating and renewable energy integration. The integration of renewable energy sources like wind and solar presents unique challenges for power transmission due to their variability and often remote locations. DLR excels in this scenario by enabling utilities to dynamically adjust line ratings. This ensures that the grid can accommodate fluctuations in energy production, facilitating the seamless integration of renewable sources. Challenges and solutions of dynamic line rating. DLR technology faces several challenges. Accurate weather data is essential for its effective operation, and coordination among stakeholders such as utility companies, regulators, and grid operators is critical. Question is: why is DLR important and why should you use it? Implementing dynamic line rating provides numerous benefits crucial for modernizing the energy sector. DLR delivers a range of advantages: enhanced safety, operational efficiency, sustainability, and cost savings that make it vital for a modern, resilient power grid. By leveraging real-time data, DLR enables rapid decision-making to prevent line overloads and faults. Furthermore, it increases the capacity of existing power lines, reducing the need for new, costly infrastructure. With the capability to adapt dynamically to environmental conditions, dynamic line rating also facilitates the seamless integration of renewable energy sources, thereby contributing to global sustainability objectives. These advantages collectively result in considerable cost savings, making DLR an indispensable tool for a resilient, efficient, and future-ready power grid. Safety enables real-time, proactive decisions to mitigate risks. Efficiency maximizes the utilization of existing lines, eliminating the need for new infrastructure. Sustainability eases the integration of renewables, supporting carbon reduction efforts. Cost savings brings economic benefits through effective line management. These benefits position DLR as a fundamental component for any power grid focused on long-term sustainability and efficiency. Harnessing the power of dynamic line rating. Traditionally, power lines have been operated under conservative ratings to ensure safety and reliability. These static values, however, often fail to consider real-time factors such as load, conductor temperature, and weather conditions. Dynamic line rating transforms this approach by continuously monitoring and analyzing these variables, determining the maximum permissible current a power line can safely carry at any given moment. A DLR system, driven by advanced algorithms and real-time data, enables grid operators to increase power transfer capacity, safely transmit more electricity through existing lines, minimizing the need for costly infrastructure upgrades. Enhanced grid reliability. Precise measurement of line capacity reduces the risk of overloading and power outages. Facilitate renewable energy integration. Dynamically adjust line ratings to accommodate the fluctuating